Welcome to lecture series on CFD part 1. This is lecture 9 on application examples for finite volume methods and error analysis. Higher order finite volume methods require special treatment near boundaries. That will be the first topic in this lecture. Described are two approaches, using ghost cells on the outer side of solution domain boundary and adapted interpolation and differentiation methods in cells along boundaries. The next topic is the implementation of Dirichlet and Neumann boundary conditions in higher order finite volume methods. The finite volume methods described in lecture 7 and 8 are then applied to one two-dimensional test case, the same one that was used for testing finite difference methods in lecture 6. Grid-dependent studies were performed with schemes of orders 1st to 4th on both uniform and non-uniform grids. In addition to the simple test code, commercial CFD software Simcenter STAR-CCM Plus was also used with its default discretization methods, as is used in industrial applications. Finally, results obtained with finite difference and finite volume methods on grids with the same resolution are compared with a surprising outcome. Higher order flux approximations refer to more distant neighbor control volumes like I-2 and I+2. Such neighbors do not exist near boundaries. This problem can be solved in two ways. One is to create ghost control volumes outside solution domain. One can then use the standard approximations for variable values and derivatives at cell faces next to a boundary, but variable values at the ghost nodes must be obtained by extrapolation using, for example, polynomial fitting through the boundary node and a certain number of internal cell centers. If a polynomial is used for interpolation, it is best to use the same polynomial to extrapolate to ghost cell centers. The other approach is to use different interpolation and approximations for derivatives at the next to boundary cell faces. They should be of the same order as at other internal faces but asymmetric. The problem is that higher order finite volume methods require variable values and derivatives not only at face centers but also in the corners. Examples of both approaches are shown in the next few slides. Here are examples of extrapolation to ghost cell centers for the 4th-order polynomial fit. From a polynomial of degree 3, fit to variable values at the boundary node and 3 internal cell centers, one obtains on a uniform Cartesian grid the following expressions for the polynomial coefficients. The local coordinate origin is in the center of the cell next to boundary. Now variable values at the ghost nodes can be easily obtained by inserting its local coordinates into the polynomial expression. This expression is obtained at the west boundary, and an analogous expression is obtained on the east side. With variable values at ghost nodes computed in this way, standard expressions for cell face values and derivatives at the first cell face parallel to boundary, as shown in this figure, can be used. As explained in lectures 5 and 8, higher order schemes are usually implemented using the third correction approach. In this case, the explicit computation of variable values at ghost nodes is not a problem, because one computes then anyway the difference between high and low order flux approximations explicitly using variable values from previous outer iteration. With ghost nodes outside solution domain, one can use the same interpolation and differentiation expressions for all inner cell faces. However, finite volume methods require derivatives and variable values also at boundary faces, but only one of them is provided as boundary condition. If the boundary value of the variable is prescribed, the gradient must be obtained from one-sided approximations. For example, we can use the polynomial described in the previous slide, take the first derivative of it, and use the coefficients and the local coordinate of the boundary node, which is minus delta x half, to obtain the derivative in x direction at the west and east boundary. When the gradient is prescribed at the boundary, we can use the above expression to compute the boundary value of the variable. For example, if a zero gradient is prescribed, the boundary value can be computed from values at the three cell centers as follows. Working with ghost nodes and higher order approximations is a bit tricky in finite volume methods. Instead of using ghost cells, one can use modified approximations at faces near boundaries. One option is to use asymmetric polynomial approximations as explained in Lecture 6 for finite difference methods. For example, if we use the cubic polynomial with coefficients defined in slide 5, the following expressions are obtained for the variable value and the derivative at face E. Because higher-order methods are usually implemented using deferred correction approach, one can use approximation based on both cell center and face center variable values in explicit flux computations. Two options are available for compact approximations of variable values at cell faces based on cubic polynomial interpolation. For this approach, face values need to be saved and updated after each iteration. Derivatives at cell faces needed for diffusion flux approximation can also be computed in a compact way based on cubic polynomial fitting. In this way, fluxes at all inner faces can be computed without reference to nodes outside solution domain. Once values at face centers are computed, one can apply the same approximations along grid lines to obtain values at cell corners, which are needed for Simpson rule integration. Finite volume approximations of convection and diffusion fluxes need to be applied to all control volume faces, including those at solution domain boundaries. At boundaries, some information about the solution must be available. One of these two options is usually applicable: known boundary value, Dirichlet boundary condition, or known gradient in a particular direction, Neumann boundary condition. If boundary value is not known but the gradient is prescribed, a one-sided approximation of the gradient is used to compute the boundary value of the variable in terms of inner nodal values as described in slide 6. Because the number of unknowns must be equal to the number of control volumes, boundary fluxes must not introduce new unknowns. Where boundary values are specified, the convection flux can be directly computed, but the diffusion flux requires a one-sided approximation of the gradient. See slide 6. One algebraic equation is obtained for each control volume. For the solution domain as a whole, a matrix equation is obtained. Let us now apply finite volume methods described in Lecture 7 and 8 to the two-dimensional test case that was used for finite difference methods in Lecture 6. We want to solve the generic scalar transport equation shown here with a known but non-trivial velocity field. Such a velocity field is offered by the so-called stagnation point flow, an inviscid flow defined by u equal x and v equal minus y. The following boundary conditions are specified: 0 values of phi at inlet, 0 gradient of phi at outlet, prescribed linear variation of phi along the west boundary from phi equal 1 at y equals 0 to phi equals 0 at y equal 1, and 0 gradient of phi in y direction at south boundary, which is the symmetry boundary condition. The main quantity of interest is the diffusion flux of phi through the west boundary. If phi were temperature, this would correspond to a heat flux along an isothermal wall. Both the integral value, that is, the total flux through the west boundary, and the local variation of flux per unit area are computed on systematically refined grids using various discretization schemes. Note that in finite volume methods, diffusion fluxes are part of the solution process, so no post-processing is required. We only need to save the fluxes for plotting or sum them up for the total flux along a boundary. The plot on the bottom shows an example of computed lines of constant passive scalar phi. A nice feature of the flow in this test case is that the flux-making velocity component is constant along a cell face. At all east cell faces, u equal x applies, and at all north faces, v equal minus y applies. This means that when computing convection fluxes, the only variable that needs to be approximated is the scalar phi. Density and velocity are both constant over each face. The plot on the left shows the computed variation of the local diffusion flux when the first order upwind scheme is used for convection and the second-order central differences scheme for diffusion flux approximation. The plot on the right shows the same information when the second-order central differences, that is linear interpolation, are used for both convection and diffusion flux approximation. Computations are performed on 6 uniform grids, the grid spacing being halved with each refinement. As expected, we see first-order convergence when the first-order upwind scheme is used for convection fluxes, even though diffusion terms are approximated using second-order central differences. The distance between curves obtained on successive grids is halving when grids are fine enough, but the convergence is not monotone. The situation is better when second-order approximations are used for both convection and diffusion fluxes. The first grid is obviously too coarse, but from 40 by 40 subdivision onwards, the expected reduction of distance between curves by a factor of 4 is evident. The lines from the 3 finest grids cannot be distinguished from each other in the plot. In this slide, the plot on the left shows the computed variation of diffusion flux when the second-order upwind scheme is used for convection and the second-order central differences scheme for diffusion fluxes. The computation is performed using the commercial software Simcenter STAR-CCM+. The results are similar to those obtained using linear interpolation in the test code shown in the preceding slide. The plot on the right shows the same information when the 4th-order central differences are used for both convection and diffusion flux approximation. We see immediately that solutions obtained using higher-order schemes are much more accurate than solutions obtained using first- and second-order schemes. Solutions from the 4 finest grids cannot be practically distinguished from each other. Here, solutions from 4 schemes obtained on the grid with 160 by 160 control volumes are compared. The first-order upwind scheme leads obviously to large errors. The solution obtained with second-order schemes, both with the test code, here labeled CD2, and with Simcenter STAR-CCM+, labeled LU2*CD2, fall practically on top of each other. Finally, the use of 4th-order central differences for both convection and diffusion fluxes leads to the most accurate solution, but the difference to the solutions from second-order methods is very small. Here, solutions from finite-volume and finite-difference methods obtained with second-order discretizations on grids with 80 by 80 in the left plot and 320 by 320 control volumes in the right plot are compared. In addition, results from the 4th-order discretization in finite-volume method are plotted for reference as the most accurate solution. We see that on the grid with 80 by 80 subdivisions, the solution obtained using finite-volume method is much more accurate than the solution obtained using finite-difference method. This is somewhat surprising, but a partial explanation might be the fact that the first computational point in finite-difference methods is at distance delta x away from boundary, where phi is prescribed, while in finite-volume method, the first cell center is delta x halved away from boundary. Thus, the approximation of the gradient of phi at the boundary, which defines the diffusion flux, can be expected to be more accurate in a finite-volume method on a nominally the same grid. On a twice-refined grid with 320 by 320 subdivisions, the differences are very small. In this slide, solutions from finite-volume and finite-difference methods obtained with 4th-order discretization on grids with 80 by 80 left plot and 320 by 320 control volumes right plot are compared. We see that on the grid with 80 by 80 subdivisions, the solution obtained using finite-volume method is more accurate than the solution obtained using finite-difference method. The difference is much smaller than was the case with second-order methods shown in preceding slide, but are still appreciable, especially for y larger than 0.5. On a twice-refined grid with 320 by 320 subdivisions, the differences are not visible. The 2 lines fall practically on top of each other. Here we are looking at the total diffusion flux through the west boundary. The local heat flux is computed at each boundary face as part of the balance for the next to the boundary control volumes. These fluxes are summed up for all west boundary faces, and the total flux is compared for 4 schemes on 6 grids. The plot on the left shows how the total flux varies with reducing grid spacing. The 4th-order scheme converges more rapidly toward a grid-independent solution, while the solution from the first-order scheme still contains a large error even on the finest grid. Estimation of grid-independent solution using Richardson extrapolation and the assumed order 2 for CDU2 and LU2 star leads to the same value on 5 most significant digits when applied to the solutions from second-order linear interpolation in the test code and second-order up-in scheme in Simcenter STAR-CCM+, minus 1.261667 and minus 1.261652 respectively. The error estimates for each scheme and grid were computed using the above grid-independent solution. They are shown in the plot on the right as a function of grid spacing. The first-order scheme leads asymptotically to slope 1. The error reduces 1 order of magnitude when the grid spacing is reduced by the same factor. The fourth-order scheme does not converge monotonically. It has a very low error on the grid with 160 by 160 control volumes, but on the next two grids, the result lies on the other side of the estimated grid-independent solution and the error changes sign. Such an oscillatory convergence is not common, but can happen. It is also possible that there is still a small bug in my code. I'll keep looking for it. If the aim is to obtain a solution with an error below, say, 1%, the fourth-order scheme reaches this practically with the 80 by 80 control volumes grid, while the second-order method, linear interpolation in the test code and second-order up in the Simcenter STAR-CCM+, requires the grid with 320 by 320 control volumes. In most practical applications, prism layers are generated near walls to better resolve boundary layers. Simcenter STAR-CCM+ generates grids automatically, controlled by one parameter, base size. The grid expands in prism layers and is often uniform away from walls. Two options were tested here. A. Constant thickness of prism layer, doubling the number of cells across the layer. Expansion factor reducing by square root, starting with 1.2 on the coarsest grid. And B. Constant number of cells, here 10, and expansion factor in the prism layer, here 1.2, with prism layer thickness proportional to base size. These plots show fractions of the three finest grids of type B near wall. They have constant expansion factor and 10 prism layers, and the prism layer thickness reduces as the grid size is reduced. Outside prism layers, the grid is uniform. In the test code, the whole grid expands with a constant factor in x direction. Results obtained with uniform and non-uniform grids are compared in the following slides. These plots show the variation of local diffusion flux along the west boundary computed using uniform, left figure, and non-uniform, right figure, grids and the test code with CD2 discretization. It is very surprising that on non-uniform grids which expand in x direction over the whole domain by a constant expansion factor, the errors become so much smaller than on a uniform grid, even on the coarsest level. Except for the coarsest grid, results from all other grids fall almost on top of each other when a non-uniform grid is used. This plot shows the variation of the total diffusion flux over the west boundary with grid refinement when second-order schemes in the test code, linear interpolation for convection, central difference for diffusion, labeled CD2, and in Simcenter STAR-CCM+ software, second-order upwind scheme for convection, central differences for diffusion, labeled LU2, are used on non-uniform and uniform grids. In Simcenter STAR-CCM+ code, an expanding grid within prism layer is used while the rest of the grid is uniform. The prism layer on the coarsest level has 10 cells with expansion factor 1.2, total prism layer thickness is 0.125 meters. The number of cells doubles in prism layer with each refinement. The expansion factor reduces to the square root of the value on the coarser grid. In both codes, the results obtained on the non-uniform grid are much more accurate than when uniform grids are used. The linear interpolation for convection terms used in the test code produces slightly more accurate results in both cases than when linear upwind scheme is used in Simcenter STAR-CCM+ code. This figure shows the discretization errors as a function of grid size. Second-order convergence is obtained on both uniform and non-uniform grids. However, errors are one order of magnitude or more lower on non-uniform grids than on uniform grids. Note that the non-uniform grid in the test code, labeled CD2, is different than the grid in Simcenter STAR-CCM+, labeled LU2 star. It is finer near west boundary, which leads to lower errors. This plot shows the variation of the total diffusion flux over the west boundary with grid refinement when Simcenter STAR-CCM+ software, second order upwind scheme for convection, central differences for diffusion, is used with a uniform and two non-uniform grids. The results from a uniform and type A non-uniform grid converge with second order toward grid-independent solution, as can be seen from errors in this plot. The two grids with prism layers along west boundary are identical on the coarser level, so the initial error is the same. However, when the type B grid is used, strange things happen. First order convergence is observed for a while, and only on the finest two grids, shown in these plots here, the slope approaches 2, but the errors are larger than when the uniform grid is used. In the uniform grid, the cells are of the same size all the way to the boundary, while in grid type B, the grid is finer near boundary. This is surprising because grid B has more cells than the uniform grid, and the cells near west boundary are 5 times thinner than when a uniform grid is used. We shall check in other test cases in lectures 19 and 20 when solving the Navier-Stokes equations whether the same behavior will prevail. Let me now briefly summarize this lecture. Higher order approximations require special treatment near boundaries. One can use either asymmetric polynomial approximations or ghost control volumes outside solution domain. For their values, extrapolation from inside is required. Solutions from finite volume methods are more accurate than solutions from finite difference method when the same grid and approximations of the same kind and order are used. The 4th order central differences for both convection, cubic interpolation for cell-phase values, and diffusion, gradient approximation at cell-phase locations based on cubic polynomial fit, lead to the most accurate solutions. Solutions on systematically refined non-uniform grids converge with second order, and the errors are an order of magnitude lower than when uniform grids are used. When prism layers are used to increase the resolution near walls, it is best to keep the total thickness of all layers fixed and increase the number of layers with refinement.